Hello, these are math notes to support your continued understanding of higher order polynomials. And so we're going to talk today about how to use the factored form of a polynomial equation. And again, how to use a factored form. Factored forms look like y equals, again, you could have some stretch factor a, and then it would be times each one of the differences between the x value and the x-intercept that is given. And so we have done this for quadratics, and we could really keep writing this for larger and larger polynomials. And so again, I'm just showing for a quadratic, it would be a times x minus the first x-intercept and then times another x-intercept as well. And so, but we're talking about higher order polynomials now. And so I wanted to separate it into two different categories because depending on whether or not you're talking about an even degree polynomial, an even degree polynomial is a polynomial kind of like y equals x squared would be a great example of that. So y equals x squared or y equals x to the fourth. And again, they can have many more terms than that, but that's the term that has the largest exponent. So all of these, again, numbers that the exponent are, they're even numbers. And so one of the things to think about is that polynomials with even degrees, in terms of what these graphs look like, if you think about what x squared looks like or what we started to understand what a x to the fourth looks like, these start and end in the same direction. And so that's a really important understanding, is that these graphs, the graphs, start and end in the same direction. And that's a super important concept to understand because it helps us when we look at a graph and we're thinking about what is the highest degree term, how we can actually generate that graph. Now, the thing is that if you have a stretch factor that is positive, that actually makes it open up. So again, if the stretch factor is positive or the a value, so if a is positive, that means it's greater than 0, then it will open up. It will open up. And so think about that as like, again, a parabola that would open up, or a fourth degree polynomial that would also open up. And also we could think about even larger degree polynomials, something like that. Now, because of the fact that they start and end in the same direction, they don't also always have to have any x-intercepts. As you know, with parabolas, they don't have to have an x-intercept if their vertex is sitting above the x-axis and they, again, have a leading coefficient that's positive. However, if a is negative, if a, again, that's the stretch factor or the leading coefficient's value, if that's negative, it opens down. And again, we can think about how it opens because of, again, it starts and ends the graph in the same direction. And the same thing that y equals negative x to the fourth, that looks kind of like an m. And we can, again, continue that extension onto polynomials that had, again, any type of even power. So I wanted to do a couple examples as well today. So you see those below. But before then, I wanted to also talk about, well, what about odd degree polynomials? As a reminder, an odd number is, for example, 1, 3, 5. One of the things that it's very important to remember is that polynomials, they are going to be any type of equation or expression that has terms that all of the powers or the exponents are whole numbers. So they're not negatives and they're not fractions. And so some examples that fit into this particular category when it's odd are going to be like y equals x cubed, or y equals x to the fifth. Those are examples of, again, odd numbers. And again, we're talking about the degree of the polynomial is dictated by the term that has the largest exponent's value. And so graphs of odd degree polynomials, the graphs, they start and end in the opposite direction. And so if you think about this, I mean, a perfect example is thinking about the graph like y equals x cubed. So again, depending on the value of a, though, they start and end in different ways. So I would like to talk about if it's positive versus if it's negative. So if your stretch factor and the leading coefficient is positive, being that it's greater than 0, then you're going to actually have it look kind of like this. So I'm going to, again, it will start in this quadrant down here, like the third quadrant. I think that's sometimes easier just to draw a graph. It will look like this. It will come down from here and end up in that fashion. So again, if it was something like a higher than third degree polynomial, it would, again, look something like that. So again, it starts down here and finishes up. Now, in comparison to that, if a is less than 0, then it's actually going to look a little different. It's going to start up here and then end down here. And again, when I'm thinking about graphs and what I'm talking about starting, again, we always read things from left to right. So that's why I say I start over here and I end down here. Or for a higher ordered polynomial, it might look something like that. So when you're looking at an equation of a polynomial, or you're even looking at a graph, thinking about how it starts and ends tells you also something about the a value that you will use perhaps to write a possible equation, or even if you have another point that your curve passes through beyond the x-intercepts, you can find that a value and find the exact equation. So let's go through a couple examples. If you are given a graph, and in this case, we're given the graph right here. This is the first example, and it also is given to you a y-intercept of 0, 3. So again, they gave you a point that it passes through 0, 3. We can write the equation starting from the spirit of factored form for this particular equation. And so if I think about maybe labeling each one of these x-intercepts, that would be really helpful to me, right? This x value right here is a negative 3. The x value right here is 1, and then that's 2, 3, 4. So the next one is x equals 4. And if you think about working backwards, that if you were using zero product property, the linear factor that would correspond to this x-intercept, that linear factor would be if I add the 3 to the other side, I would get x plus 3, right? Equaling 0. And so therefore, that's how we figure out that linear factor. But of course, there are 1, 2, 3 linear factors that will correspond to this graph. And the other thing that I wanted to say here is that this graph, we've learned about that this is a bounce off the x-axis. And what that indicates is that implies that there's going to be a squared linear factor that corresponds to that particular x-intercept. And so I can use all these pieces of information as clues to write the equation. And so I'll see if I could squeeze it into this little tiny area. I've got a, because I don't know what that is at this point, and then I've got x plus 3 squared, and then I've got this other x-intercept that's going to correspond to an x minus 1, and finally the x minus 4. And I just barely squeezed that all in there. But this would be a possible equation. But you can actually write the exact equation for this, and the reason is a couple of, is because we have another point that it passes through. Remember, you can't plug in one of the x-intercepts because that actually won't allow us to find a, but if you substitute the 0 for x and the 3 for the y, then we'll be able to find the exact a value. And so I'm going to go ahead and do that. I'm going to try to do it in a different pen just to see if I can save space. I've got 3, right, for the y value equals a times, and if I substitute in that 0 here, I got 0 plus 3 squared times 0 minus 1 times 0 minus 4. And thinking about simplifying this perhaps in one step, I've got 3 equals a times, and this would be 9 times negative 1 times negative 4. Those two negatives will become positive. And so this is saying 3 equals a times a positive 36. And so if you divide both sides by 36, you would get a equals 1 over 12, since 3 goes into 36 12 times, but since you're dividing both sides by 36, it's 1/12. So my final equation here is y equals A times X, oh, I don't need A anymore. I've calculated A to be, again, 1/12. 1/12. And then we have got the X plus 3 squared times X minus 1 times X minus 4. And that's my final equation for this particular graph right here. One thing I wanted to note is that this is a 4th degree polynomial. Again, right here, I've got an x squared, an x, and an x, and all of those, if you multiply this out into a standard form, would have an x to the 4th. And notice it looks a little bit like a w, as all x to the 4th functions do. And again, it starts and ends in the same direction because it's an even degree polynomial. And again, since the a value is positive, it should open up. And those are all the things that you want to really think about in your mind as you're like finalizing. That this equation does match this particular graph. That concludes the first part of the notes for now. I would like you to ideally listen to the next video where I will go through writing the equation for the next couple graphs.